So ions are created by the metal. So the metal gives electrons to the non-metal. And as a result, we have a positive, what's that called? Cation. And a negative? Anion. Good. And they are attracted, right? So these two are attracted to each other. Attracted. And what do we call that? With what kind of force? Or interaction? Electrostatic, or good, so electrostatic slash, let's see, Coulombic, right? Coulombic forces. Anytime you have a Coulombic interaction or electrostatic interaction, it means opposite charges, positive, negative. That can be protons and electrons in an atom, but in a bond or a compound, you have cations and anions for ionic. So that's the gist of ionic bonding. It's usually a metal, non-metal. Sometimes it's not always that cut and dry. For example, NH4Cl is ionic. There's no metal. That's positive, that's negative. They still use cations and anions. So again, nothing in here is ever really cut and dry or black and white.
Pardon the interruption. Can we please have middle school student senate?
All right, so that's the moral of the story. Electrons transferred, positive, negative interaction. Okay, what does the Coulombic force, let me make sure I'm not going off the reservation here. What does the Coulombic force depend on? Two things. So this strength, the strength of this force will go up if the ions are close together. So the closer the charges equals an increase in Coulombic force. Radius size has to do with that, right? The size of the ion, radius of the ion affects that. And then what's the other thing?
Charges themselves.
Right, the magnitude of the charge. So magnitude, so like a +2 versus a +1. Magnitude of charges. Help you understand this. Very simple manipulative, we call it. It's a fancy term. If I can get in here. Okay. I don't have two of them, but that's okay. I have two basketballs. Perfect. Okay. Let's say I have two ions the size of basketballs. Okay. Just to really give you a visual here, understand the concept. So let's say the center of the basketball would be the nucleus. Let's say this is a cation, this is an anion. So two really big ions get together. Are the centers of the nucleus, of the nuclei here and here, close together? I have to compare it to something else, but I'm going to tell you no, it's not. Because these are so big, this is as close as they can get, that the nuclei are this far apart. Would you agree with me?
Yeah.
Okay. If you have two really small ions, aren't the nuclei very close together?
Yeah.
Okay. Oh, that was kind of cool. Oh. Get it, Dylan.
Bounce it off the desk too.
Okay. Trying to hold it. I don't know if I can do this. Okay.
Okay.
The concept here is from here to here. So you're
Pardon our final announcement. Can we please have local history club and ski club?
hold it. So
Ski club.
are you really?
Yeah, there he is.
So the nucleus of this ion and this ion, the nuclei are very close together. So this here, what we need to write down somewhere over to the side or underneath it, or you can go ahead, that the smaller the radius, the closer they can get together, right? So I'm gonna write that. So the smaller the ionic radius, results in the ions getting closer together. And that means stronger forces. Does that make sense? Because remember, it's the protons of one attracted to the electrons of the other. That's a covalent bond, and the ionic concept is the same thing. So if you have a positive negative charge, they can get really close together here. But if they're big, they can't get as close together. The nuclei, they can't get as close. So that should make sense. Those in there, those there. Okay. All right. So what about the charge? So if you have a +2 and a -2 versus a +1 and a -1, we would expect this to have stronger Coulombic force. So that would be a stronger ionic bond. So it's really just about those two concepts. The radius size, that's how close they can get together, and then the charge itself, the magnitude of the charge. Makes sense? Okay. Now, we're going to talk about this thing called lattice energy, which actually isn't in the good old AP Chem Bible there, but you do need to understand the concept here. So I'm going to show you a picture. I want you to sketch this down in your notes. This is what a crystal lattice structure looks like for ionic bonds. So a lattice structure, because ionic bonds form a 3D. Here we go. You did hook me up. Lights, please. Oh. Well, he hammered on it a little bit. He has to. If it comes out, then it would be kind of like a hazard, we'll call it. So it has to be closer to the wall. Okay, write that down. That's what salt looks like. Okay. So here's how I worded it here. Let's see. Ionic bonds created from the net attraction between oppositely charged ions closely packed together in a crystal lattice. That's just the actual wording from the AP Bible there. So, closely packed together in a crystal lattice. This is a crystal lattice. It is repeating over and over. Why is the Na smaller than the Cl? Don't say atom. Ion, thank you, Marcy. It's an ion, smaller ion. Na plus has how many electrons? I know it's the day before a little mini break, but you can do it. 10, thank you. How many electrons Cl minus have? 18, right. So Cl minus has a larger radius than Na plus. But the Na being so small helps the attractive forces here, because it can get a little bit closer. Another way to word this here, the cations and anions arrange themselves in a 3D array that maximizes attractive forces and minimizes repulsive forces. What does that mean? You guys still busy on drawing your picture here? It doesn't have to be perfect. Right, Kira? I was going to say it doesn't have to be perfect, Kira. But I'm sure it is.
I mean, that's about as good as
The cations and anions, so look up here if you can, look up here while I say this. Cations and anions arrange themselves in a 3D array that maximizes attractive forces and minimizes repulsive forces. So what does that mean?
NAs don't connect to NAs and CLs don't connect.
Good. It arranges itself naturally in the most efficient packing. That's what it's called. And there used to be a whole section on AP of the unit cell and what these crystal lattice look like, and there's different shapes to different lattices. They took that out because it doesn't, and they word it, they say they took it out because it doesn't increase the, doesn't lead to a deeper understanding of ionic bonding. It doesn't. It was just memorizing what crystals they are. So here's the concept. The NAs and the CLs from different layers, if you will, different levels, aren't going to line up next to each other. So an Na will never be directly above or below an Na. Why? What would it do? Propel. Same thing with the CLs. That's what it means. It arranges itself in a crystal structure that is efficient and maximizes attractive forces. There's another way to look at it. This is actually what's called a unit cell. It's like these little cubes. If you could take out one little cube of a whole big pile of salt, this is what it looks like. Okay, so there are slight spaces in there. They're not literally right on top of each other. There is slight spaces because remember, there are repulsive forces between electrons, but that's another way to look at it. Okay, so that's the crystal.
So that's basically what 1 grain of salt would look like if you were.
Not 1 grain, 1 unit cell. Actually, is that even a unit cell? I have to count the atoms. How many CLs are there? Yeah, that's a unit cell. So that's 1 unit cell of 1. How would I explain that? No, it's not a grain of salt. It's a really, really small piece of 1 grain of salt. Okay, that's the easiest way I can say it right now for the sake of time. All right. So let's see. We talked about that. So technically, we wrote this in our notes before. I got to make sure I cover all my bases here. So the Coulombic force is directly proportional to the charge of each ion, but inversely proportional to the square of the distance between the centers of the ions. That shouldn't ring a bell. That's the equation for Coulomb's law. You don't need to know that. You don't need to like spout that off or recite that. Basically, if they get closer together, they're going to be more attracted, and if you have more positive, more negative charge, they're going to be more attracted. This we need to write. This we need to write down. Ions with higher charges lead to higher Coulombic forces, therefore higher. I already said that. Ions with higher charges lead to higher Coulombic forces, and therefore higher. What do we do in chemistry if we want to find out if something is held together with strong forces? We just did it in lab. You try and see at what temperature it melts. Right. So if it melts at really high temperatures, that means it has strong Coulombic forces. So the higher the charge, the stronger the Coulombic forces, and that means higher melting points. That's what lattice energy is. So lattice energy is the energy required to dissociate ionic bonds. So I have the actual definition here. So lattice energy, and as long as I give you the definition and have a couple minutes to kind of explain it, you should be able to do the homework. You might need to look some things up in the book though. Energy required to completely separate 1 mole of a solid ionic compound, which is a lot of energy. That's a lot. So that's like 58 grams of salt. That's a lot of salt. Energy required to completely separate 1 mole of solid ionic compound into gaseous ions. And the higher the lattice energy, higher the lattice energy equals higher melting points. So this is kind of like the first new stuff. You kind of learned all the other stuff in Regents, just we didn't really go as much in detail, but that's kind of the gist of it. So let me give you some examples here. Okay, so everything we've already said explains this. So if you have higher charges, +2, -2, higher lattice energy. If the atoms are smaller, ions are smaller, closer together, higher lattice energy. So that all of that already plays into this. Let me give you an example here. NaF has a lattice energy of 904 kilojoules per mole. Real quick, just write this one more example down. And CSF has a lattice energy of 757. And real quick, the explanation here, Na plus is way smaller than CS plus because CS has 6 energy levels and Na has 3. So this is going to be stronger because of everything we just learned. So that's all I got. You got those 5 problems due Monday. We'll pick up with this on Monday. Today was a little weird, but that's okay. We persevered. We got through it.